Hi everyone, my name is Glenn Lipscomb. I'm a professor in the Chemical Engineering Department at the University of Toledo. It's a great pleasure to talk about our work on the effect of packing non-uniformity at the fiber bundle case interface on flow distribution and separation performance of hollow fiber membrane modules. This is work that's been done here at the University of Toledo in conjunction with two students. Lily's son is a graduate student and Adabong Etienne is an undergrad. It's work that's been supported by the Department of Energy through the National Energy Technology Laboratory with the assistance of Leidos Research Support Team and Oak Ridge Associated Universities in managing the grant. Before I begin, I just want to thank the organizers for this great opportunity to speak and for the wonderful job that they've done converting what we had hoped would be a live in-person meeting to a virtual meeting. The presentation today will consist of the following parts. We'll start off with a brief motivation for the work, then talk about, in general, the flow distribution challenges that are faced in hollow fiber membrane modules, then talk about, in particular, fiber packing near the case, and then how fiber packing affects module performance. The motivation for this work comes from comparison of experimental measurements of module performance to theoretical predictions, assuming ideal module contacting. And the example shown here is one in which a hollow fiber membrane module is used to produce nitrogen from air. Air is compressed and fed to the lumens of this hollow fiber module. As the air flows through the lumens of the fibers, oxygen permeates preferentially relative to nitrogen, leave behind a nitrogen-enriched stream. One of the key performance metrics when quantifying the performance of these modules is the ratio of the product flow rate, the nitrogen flow rate, to the feed, which is referred to as recovery, how that depends upon the oxygen concentration of the product of the retentate. And theoretically, if you assumed you had an ideal countercurrent module, you would expect to see performance that would follow along this green line right here. However, experimentally, especially when developing modules from a new material, developing modules for the very first time out of a new material, what you find is that when you do experiments on these modules is that the recovery curve, the dependence of recovery upon the oxygen mole fraction, follows this red line. And that two things are noticeable here. First is that for a given oxygen concentration in our product stream is that the recovery is less than what we had hoped. Secondly is that we can't go to arbitrarily low oxygen mole fractions. There seems to be a limiting oxygen mole fraction that we can produce. Whereas theoretically, for a pure countercurrent module, we should be able to go down to close to zero. Even worse is that in some experiments, what we find is that as you decrease the oxygen concentration of the retentate is that you reach a limiting value before the flow coming out of the module goes to zero. And you see that as you continue to reduce the flow coming out of the module, instead of the concentration decreasing, the concentration increases. So the question is, what gives rise to this type of performance, these performance inefficiencies? The performance inefficiencies that were observed in the last slide can be attributed to a number of different factors. Certainly, if you don't have sufficient quality control in the membrane manufacturing process, then you have large variability in membrane properties, in membrane permeance and membrane selectivity. You could see some significant decreases in performance. But there are another whole host of factors that are associated with flow distribution effects. How do we get fluids or gases into and out of the module? These effects can arise from problems with the tube sheet, which are imperfections that don't separate the lumen and shell flows. They can arise from problems associated with getting the fluid or gas into and out of the fiber lumens, which we're not going to talk about. There's a set of factors associated with the fluid distribution to the shell, and we're going to focus on those for the rest of this talk. Among the factors that are associated with flow distribution effects in the shell, we're going to focus on a potential impact of a gap between the fiber bundle and the case. What's illustrated over here on the left is a randomly packed fiber bundle within a circular case. And what you can see in these green regions that are highlighted here is that there are gaps that exist between the fiber bundle and the case. The question is, what is the impact of these regions on performance? And we've done experimental measurements of flow distributions within the case in order to see how much fluid does flow there and what could be the potential impact of that. These were measurements made with an artificial kidney, a hemodialyzer, in which we introduce into the shell through the distribution port right here at the top and then into the manifold a fluid, in this case water, containing a CT contrast agent, and we watch where it went. And these three images that you see here from top to bottom represent images taken after certain periods of time from changing from just pure water flowing through the shell to having water plus the CT contrast agent. And what we see in all cases is that after the fluid with the contrast agent fills this distribution manifold that extends around the fiber bundle from the top to the bottom here, is that the fluid flows preferentially at the gap at the interface between the bundle and the case. You can see these white lines that extend out from both the top and from the bottom in this particular cross section. And you see this in all the other subsequent images. And in fact, you see the fluid at the top of the case here, at the gap between the fiber bundle and the top of the case, actually exits the lumen manifold well before we fill in most of the module. So what is the impact of having this type of performance, this type of velocity distribution within the fiber bundle? What is the impact of that on performance? It's not well understood for liquid separations, and it's less well understood for gas. And so what we're interested in is trying to characterize the performance initially not in a randomly packed bundle, but in a well-packed bundle, either a square-packed fiber bundle or a triangular packed fiber bundle. And we put these inside a case, we put these into a circular case. What we're going to see is that there will be regions where the fibers are not uniformly packed up against the case. And but at this point, we're not going to consider a bundle like this in which we have a circular case. What we're going to do is assume that we just have a rectangular bundle and that these fibers are packed up against a flat surface like this, a planar surface like this, for both regular square packings as well as for regular triangular packings. And the question we're going to ask is, what is the effect of having these fibers at different distances, this closest fiber being at a different distance from the case wall here? What effect does that have on performance? Before presenting the results, I want to talk about the terminology we use here. Over here on the left, you see some of the terminology to indicate the dimensions of the problem. This uppercase D represents the distance from the no-slip wall up to the center of the very first fiber. The lowercase d is the distance between the center of fibers, which is related to the fiber packing. Finally, R represents the radius of each fiber. Over here on the right, we also show how we're going to talk about calculations of velocity and of flow rate in two different limits. One is we're going to talk about what is the flow rate around the fiber closest to the wall. We're going to refer to that as Q wall. And the shaded region you see here is the region in which we're going to be calculating the flow rate and calculating an average velocity to represent the velocity or the flow rate at the wall. We're also going to be talking about the flow through a stack of fibers like this, and we're going to be varying the number of fibers that we stack up to look at the effect of that. But if we calculate the total flow rate to the stack of fibers we're considering, and we take that and divide it, that will be the Q total here. We divide that by the area available for flow with an average velocity through that region there. What we're going to be doing is simulating well-developed velocity fields within these fiber bundles in the axial direction, assuming the fibers are all aligned perfectly axially. And in these simulations, we're going to consider a little section here, a little cross-section here that you see, in which we're going to apply symmetric boundary conditions along the center line through the stack of fibers, as well as along the line here to the right. We're going to assume that we have no slip here at the wall adjacent, where the fibers are adjacent to the wall. And then finally at the top, we're going to assume that we have a symmetric boundary condition because this represents 1/2 of this rectangular bundle. Here are the predictions of the velocity field. This is once again the well-developed axial velocity field for, on the left over here, a square packing, and on the right, a triangular packing, in which we varied the fiber packing fraction between the two, as well as the ratio of the distance of the first fiber to the wall relative to the fiber radius. So the images over here on the left are for a square packing, in which we have a relatively high fiber packing fraction of 0.6 and a D over R of 2. And you can see here, if you look closely adjacent to the wall, is that we do have these hot spots where the velocity is much higher than it is if we look at the spaces in between the fibers well above the fiber wall here. So the question is, how large is this velocity down here, and what would be the potential impact of having this high velocity region on overall module performance? One would expect that as you increase the number of fibers and that you make larger and larger modules, this effect will become smaller and smaller. Same thing we observe with a triangular packing over here. This is for a slightly lower packing fraction of about 0.4, but for the same D over R of 2. What you can see here is we do have these hot spots where the velocity is much higher adjacent to the fiber wall, and that as we increase the number of fibers, as we go from just 1 to 10, is that we see that this hot spot remains here. But that as we look at as we move up the stack of fibers we have here, is that the differences between subsequent fibers in terms of the velocity field around it becomes smaller and smaller. Eventually, as just mentioned, is that if we include or examine a very large stack of fibers here, we expect that the effect of this region down here would not be too important. To validate the predicted velocity fields, we calculated the axial Darcy permeability for different fiber packing fractions for square packings, and the results are shown here in this table. You can see for fiber packing fractions ranging from about 0.3 to 0.7, the values we calculated for the axial Darcy permeability are in good agreement with those reported previously in the literature from both Bao and Sangani. What's illustrated here is the average velocity that was calculated for the flow around the fiber closest to the wall, as well as the average velocity for the flow through the entire stack of fibers that was considered as a function of fiber number. Both of these figures are for square fiber packings for two different values of the fiber packing fraction. The figure on the left is for a packing fraction of 0.4, and the figure on the right for a packing fraction of 0.6, both for a D/R ratio of 2. So the distance from the wall to the center of the fiber is 2 times the radius of the fiber. If you look at the figure here on the left for the value of packing fraction of 0.4, what we see is that as we increase the number of fibers that we consider in the simulation, remember this is a symmetric bundle, so we're looking at 1/2 the bundle. We can flip the stack up around the horizontal line at the top to get the full bundle. Is that if we look at the average velocity in the region around the fiber closest to the wall relative to the velocity that we would see around a fiber in an infinite bundle, is that it doesn't depend upon fiber number, first of all, and that it's slightly larger than the average velocity for a fiber infinitely far from the wall or in an infinite bundle. In this case, the velocity in that region is only about 3% higher. If we look at the total flow rate and the average velocity through the total stack of fibers, we see is that starts off at a slightly larger value than 1, but then decreases fairly rapidly as we increase the number of fibers from 1 to 10. This is the figure here on the left. Figure 3 is for a packing fraction of 0.4. What we see is that this changes dramatically if we go to a packing fraction of 0.6 in the figure here on the right. Is that, like as we saw for the lower packing fraction, is that the velocity in the region around the fiber closest to the wall stays relatively constant. The flow rate in that region stays relatively constant as we increase the number of fibers that we're considering, but that the average velocity in the whole stack of fibers initially starts off at a much higher value, as well as the velocity adjacent to the wall of a value close to 3, and then it too drops off fairly rapidly as we increase the number of fibers. What's shown in this slide is the value calculated for the average velocity through a stack of fibers for a triangular packing, the average velocity for that stack relative to the average velocity we would expect in an infinite bundle, as a function of fiber number, as well as for different values of D/R. D/R being the distance from the wall to the center of the fiber closest to the wall, relative to the radius of the fiber. What we see is that in all cases is that as we increase the fiber number, the values of the average velocity through the stack approaches that of an infinite bundle as we go to high fiber numbers. This increases well above 1. We see it approaches 1 from 2 different limits, though. It approaches 1 from a value less than 1 when we have fibers close to the wall, in this case for D/R equals 1, and it approaches from a value greater than 1 when we have D/R large, such as D/R equals 8, from 2 to 8. Somewhere between 1 and 2, what we see is that there will be a minimal effect of the fiber number on the calculated velocity. What's shown over here in the figure on the right is the ratio of the average velocity around the fiber closest to the wall, and in this case it's slightly different for the triangular packings. It's calculated for this area that you see illustrated here, that's shaded here. This is the average velocity in that region relative to the velocity for you would expect within an infinite fiber bundle. This is a function of fiber packing fraction down here on the x-axis, as well as a function of D/R. What we can see is that the velocity in the region adjacent to the fiber closest to the wall can be several hundred times larger than the average velocity in the bulk of the fiber bundle if we have D/R values that are approach 8. The question is, what effect does this velocity variation have upon performance? And we approach this from the point of view is that can we potentially define equivalent flow channels through which we'll monitor the flow and calculate the mass transfer that occurs, and then add up the contributions from each of these equivalent flow channels in order to get the whole module performance. And so the particular case that we're looking at is one in which we're considering capturing CO2 from flue gas. And you can see here we're considering a membrane that has a CO2 permeance of about 1500 GPU and a selectivity of 75. So that might be typical or might be considered for a CO2 capture membrane. And for a feed pressure of 2 atmospheres, we're going to, in a feed concentration of 0.2, a CO2 mole fraction of 0.2. What we're going to do for these simulations is assume that we have a vacuum on the permeant side, so we don't have to account for the flow or the compositional changes that occur there. The way we're going to approach this problem to simplify it is that we're going to take the velocity fields that we calculated for these stacks of fibers, and then we're going to find an equivalent flow channel around each fiber. So for instance here, for a square packing, we'll find an equivalent flow channel as shaded here, called Q1. For the first fiber, we'll define an equivalent flow channel for the second fiber, which is around the second, as you can see here, shaded around the second fiber, as well as for the third fiber, etc. We're going to do the same thing for the triangular packing. As you can see here, we're defining an equivalent flow channel around the first fiber, second fiber, third fiber, etc. What we're going to do is we're going to, from our well-developed axial flow calculations, determine a feed flow through each of these channels, calculate mass transfer due to permeation across the membrane and the changes that will occur then in composition and flow through each of these flow channels. And then we're going to mix the gas all together that comes out of each of these flow channels in order to calculate the overall module performance. Now, the question ultimately is going to be is dividing this problem up into a set of parallel non-interacting equivalent flow channels. How good of an approximation is that? And we're going to look at that in a moment. So here are the predictions of retentate recovery. This is the ratio of the retentate flow, this is the flue gas. You can think of this as a flue gas that's had the CO2 removed from it as a function of the concentration of CO2 in that flue gas. So ideally, we'd like to bring this concentration of CO2 down low. We like to recover the CO2 for sequestration. And what's shown here are two figures, illustrating the recovery as a function of the CO2 composition for modules with different fiber numbers. And we're going to refer to these simulations where we have this assumption of non-interacting equivalent flow channels as our 1D approximation. But we're going to compare the results here for two different cases. On the left, we have a D over R equal to 3 and a packing fraction of 0.4. And on the right, we've increased the packing fraction to 0.6. In each case, there are several lines shown. The line labeled infinity, the squares here represent what we would expect through a uniformly packed bundle in which there's no effect of poor packing adjacent to the case. And then we compare that to the calculated performance that we would get for different numbers of fibers adjacent to the fiber wall that form our rectangular bundle here, ranging from 10 to 200. And what we see in the case on the left over here, where we have a packing fraction of 0.4, is that there is a small decrease in performance, that for a given CO2 concentration in the retentate is that we see a reduction in the recovery of the nitrogen in this case that we're leaving behind. We see a small drop for 10 fibers, but that decrease goes away as we increase the number of fibers to 50 and is virtually non-existent as we go to 200. This is for the case where we had the packing fraction of 0.4. If we increase the packing fraction of 0.6, we see quite a bit different case, is that we see the same relative transition, is that if we compare a small number of fibers in our simulation, say 50, we see a larger drop, in this case a much larger drop relative to the case in which we had a packing fraction of 0.4, that as we increase the number of fibers from 50 to 100 to 200, is that we see these curves move toward the curve we would expect for a uniformly packed bundle with no gaps between the fiber bundle and the case. Well, how good of an approximation is that? Making the approximation dramatically simplifies the calculations that are required, the simulation effort that's required, but is this a pretty good approximation? It's one that's commonly been made in order to calculate mass transfer coefficients in both regular and randomly packed fiber bundles. How good of an approximation is it here for gas separation? And so to evaluate that, we did full three-dimensional simulations of flow within a square and a triangular packed fiber bundle, a planar bundle, in which we calculated the full velocity field and the concentration fields that would exist as gas was transferred from the feed across the fiber wall due to permeation into the fiber lumens. What's shown here is the concentrations of gas, of CO2 in this case, within the the shell within the gas flowing around the outside of the fibers. What we can see is that this region here adjacent to the fiber wall, between the fiber wall and the first fiber, is that we see much higher concentrations of CO2 in here, that this channel right here acts like a bypass channel in which we have very high flow rates and we have reduced rates of CO2 capture from it. Well, from these simulations, what we're going to do is we'll be able to assess the interaction that occurs between the fibers and whether this equivalent flow channel approximation is appropriate. Before doing the comparison, we wanted to establish that this does give us the correct results for a single fiber in an infinite bundle, a well-packed, in this case, square bundle. And what we see is we compare the retentate recovery, the flow rate of the flue gas in which we've removed the CO2, the flow rate of that gas that we're going to exhaust as a function of the concentration of CO2 in that stream, is that we get very good agreement between the 1D, this is a one-dimensional simulation using a spreadsheet, versus the 3D simulations performed using COMSOL multiphysics. Comparisons from the full 3D simulations and the equivalent flow channel calculations are shown here for a total of 50 fibers in a stack for a square packing. Looking at these figures, which are plots of the retentate recovery as a function of retentate CO2 mole fraction, you see the agreement between the full 3D simulations and the equivalent flow channel calculations are in fairly good agreement. The top two figures are for a D/R value of 3 and a fiber packing fraction of 0.4 on the left and 0.6 on the right. Same fiber packing fractions are shown on the bottom, but for a D/R value of 8. The one case that we have the greatest deviations are in the case of, in the upper right-hand corner here, of a D/R of 3 and a packing fraction of 0.6. Here we see that the 1D equivalent flow channel approximation gives us a slightly larger decrease in the recovery than the full 3D simulation does. Given this observation, it would be reasonable to assume that the 1D approximation will give you an upper bound on the reduction in recovery that you would expect. Similar comparisons are observed when we increase the fiber numbers in the stack to 50. Well, is there a way to improve the one-dimensional equivalent flow channel approximation by combining it with not a full 3D simulation, but a 3D simulation of a portion of the bundle? And that's what's shown here, is that, first of all, let's look at this red circles here represent the simulation of a bundle in which there's 200 fibers, a full 3D simulation. And the black squares here represent the 1D equivalent flow channel approximation. We can see there is some differences between the two. And we'd like to try to eliminate those to reduce that with minimal increase in computational complexity. What we can do is, the approach that we took is that let's simulate the flow through the first, say, 5, 50, or 100 fibers adjacent to the wall, and then use the 1D approximation, the equivalent flow channel approximation, for the rest of the fibers. And what we see is that as we can choose as few as 5 fibers and do the full 3-dimensional simulation, combine that with the 1D approximation for the remaining 195 fibers, then we get very good agreement with the full 3D simulations. So this offers a way to reduce the computational complexity while accurately calculating the interactions that occur between flow channels. And finally, this shows a comparison of the predictions for an infinite fiber bundle as well as the 1D and 3D, the full 3D simulations and the 1D equivalent flow channel approximation for a triangular fiber packing. And we find similar results as what we found for square packing. And that we see a reduction in the recovery for a given CO2 mole fraction in the retentate product. And that as we increase the fiber numbers, is that the differences between the 1D and 3D calculations and the infinite bundle decrease. And finally, let's compare the triangular packing results to the square packing results. In this set of figures here, what we see is that these are comparisons for different numbers of fibers for a D/R of 3 and a packing fraction of 0.6. And we see in that all cases is that the square packing, the blue triangles here, give slightly better performance than the triangular packing. And this is primarily due to the fact that the triangular packing leads to larger gaps that exist adjacent to the wall. And so with that, I'd like to conclude is that for Poor fiber packing near the wall can dramatically impact the velocity field and ultimately the performance of a gas separation module in which we feed the gas to the shell. We expect similar effects if we were to introduce a sweep, and that this impact increases with fiber packing fraction. This effect can extend hundreds of fibers, which if you go through the calculation, assuming a fiber size of anywhere from say 200 to 300 microns, this can be on the order of tens of centimeters. The equivalent flow channel approximation, which requires that you only know the well-developed axial velocity field, agrees well with the full simulation, but can be improved even further by including only a small subset of fibers adjacent to the wall, closest to the wall. And finally, is that what we found is that for the performance predictions for square packing were better than those for triangular packing. And with that, I'd like to thank the Department of Energy and the NETL, the National Energy Technology Lab, for their support of this work, and to acknowledge that this work represents the views and opinions of our research group, not necessarily those of NETL. With that, thank you. I look forward to your questions and comments.